We're continuing on with Chapter 7, which again are applications of integration. And this is a video on Section 7.6 involving moments, mass, and centroids. It might be wise to read the first part of this section a little bit so you can kind of get an idea of what's going on. But the primary thing we're going to talk about are moments. And this is the tendency to cause movement around a point of axis. And the definition of a moment is here, which is mass times the distance. And one thing we're going to talk a lot about are basically like when items are in equilibrium. So there's something called the fulcrum, which is basically the origin. And essentially what will happen is there will be some sort of weight here and then another weight here, and we want to figure out when we are in equilibrium. And equilibrium is when the moment on the left is equal to the moment on the right. So essentially what this means is mass 1 times distance 1 is equal to mass 2 times distance 2. And that's what we'll be working with. There is a table of commonly used measurements of mass and force with their conversions in the text, so you might want to check that out. Here's our first example, and it says consider a beam of length L with a fulcrum or the origin x feet from one end. There are objects with weights W1 and W2 placed on opposite ends of the beam where weight 1 is less than weight 2. We want to find the value of x, this here, so it's going to be a distance, that the system is in equilibrium. And then we're given more specific information here. So this is kind of like a teeter-totter, you can think of it. And two children weighing 48 pounds and 72 pounds are going to play on a seesaw that's 10 feet long. So we know that this whole distance is 10 feet. If weight 1 is less than weight 2, then that means this child is 48 pounds and this child is 72 pounds. Do not confuse a box with a child. They are very different things. So if we want to identify when we are in equilibrium, as indicated on the previous slide, we want M1 x1 to equal M2 x2. So let's focus on these two sides. On the left-hand side, our mass is 48, and the distance, we don't know the distance to the fulcrum, and it is referred to as x. On the other side, our mass is 72 pounds, and this distance is L minus x, where L represents the length of the entire beam, or seesaw in this case. So 10 is L, so my length is 10 minus x. And then we simply solve this and find x. I'm hopeful that you can do this simple algebra. So we will add 72 to both sides. Over here we get 120x is equal to 720. Divide by 120, and x is 6 feet. We know we have feet because of this here. So since we are asked to find an x such that the system is in equilibrium, what this means is there will be a balance when The 48-pound child is a distance of 6 feet from the fulcrum, or the center. So if the 48-pound child is 6 feet from the fulcrum, then the 72-pound child is 4 feet from the fulcrum, because 10 minus 6 is 4. Of course, this can get a little more complicated. So here we're talking about a center of mass of a two-dimensional system. So it's a little more complicated and not a linear system. But here we have a two-dimensional system like a coordinate plane, an XY axis. And here, one thing to think about is, in general, a moment about a line, so whether it's the x-axis or the y-axis in this case, a moment about a line is the sum of the product of the masses and the directed distances from the points to the line. And here's what I mean. If I'm looking at this first mass here, then I need to identify what that weight is. But then this x1 or even this x2, so on and so forth, this is the distance from the y-axis, because we're interested in the moment about the y-axis. So the distance from the y-axis is this here, which happens to be x1. So that's where all of these come from. We represent this as m sub y. Similarly, if I want the moment about the x-axis, I take these masses and I multiply those by y values, because those y values are the distances from the x-axis. So if I'm looking at this, here's the x-axis. This is the distance of the mass from the x-axis, which is a y value. And we will represent that as m sub x. So if we want to identify the center of mass, it's represented in this way, where x bar is found here and y bar is found here. The last thing to take note of is how we find m. M is the sum of the masses. Okay. Now, in this example, or in this next example, I'm just going to do the center of mass of a linear system. So it's just kind of taking baby steps. So let's take a look at that. In this example, we are asked to find the center of mass. And recall, if we are trying to find the center of mass from the previous slide, that's x bar, y bar. And sometimes we need to find both, and sometimes we just need to find one. But this is a linear system because it's lying on the x-axis. So since all of our masses are on the x-axis, in this case, we are simply looking for x bar. Now, if you refer to example 3 in your text, this will give you an example of a two-dimensional system in which you'll have to find x bar, y bar for the center of mass. But here we just have a linear system on the x-axis. All right, so we have these different masses located at these different x values. So it says that x1 is -2, which is right here. So this is where our first mass is, and it's a weight of 8. Then we have the second one at a value of 6, or a distance of 6. So that is here, M2. M3 is at 0. M4 is a distance of 3. And then finally, M5 is at -5, which is here. Okay, so really what we want to do, if we want to find the center of mass here, we want to find the distance from the y-axis. So what we're doing in this case is we are finding the moment about the y-axis. If these are all on the x-axis, we are finding the moment about the y-axis. So let's use our formula and see what we can do. So we are finding m sub y, and that is found by taking the weight times its distance. So the first one is going to be 8 times -2 plus 5 times 6 plus 5 times 0 plus 12 times 3 plus 2 times -5. So we can just plug all this into the calculator and we will find that m sub y is equal to 40. So now what we need to do, according to our formula, is we need to find m, where m is just the sum of all the masses. So we just add all of these up. 8 plus 5 plus 5 plus 12 plus 2. This gives us 32. So in order to find x bar, remember from the formula, x bar is m sub y over m. So in our case, we have 40 divided by 32, and this simplifies to 5/4. So the center of mass in this case is 5/4. Since this is a linear system, we only need to find x bar. Now, there are occasions in which we want to find what's called the centroid, and that's the center of an area, and so no density is involved here. So if that's the case, it is referred to as a sub x, which is the area times the distance from the y-axis. And so these are essentially x values. On the other hand, a sub y is the area times the distance from the x-axis, which are the y values. And area is just found by the area of the region. So the centroid of a region is found by this here. So x bar is found by taking a sub x divided by the area of the region, and y bar is found by taking a sub y divided by a. Sometimes this is referred to as the center of mass of a planar lamina. Here's our first example. It says, introduce an appropriate coordinate system and find the center of mass of the planar lamina. And of course, the answer will depend on the position of the coordinate system. So what we need to do is we need to come up with where we're going to put this on a coordinate plane. Now, I would recommend placing it in the first quadrant and having this here be the origin, just for simplicity's sake. Now, if I do that, and based on what I see here, I know that this is 1, 2, 3, and 4. Here, this would be 1, 2, and 3. Okay, now what I want to do is I want to break this region into smaller shapes. And in this case, I would recommend making these into different rectangles. So when I do that, I'm going to have 3 separate rectangles. And I want to find the center of each of these rectangles approximately. So approximately the center here and let's call this M1. Here's the center of this region, call this M2, and about here would be for M3. So the first thing we want to do is we want to find the centroids of a given region. So essentially what we're going to do is we are going to try to find the coordinates of each of these centroids. So here, if I'm looking at this, and my markings are slightly off, but I would say that this here, if I wanted to find this approximate x value, it'd be a half. And then this approximate y value here, well, we know that this is 3 here. So half of that is 3/2. We're going to do the same thing for the second region. The second region, the x value is 2 for this ordered pair, and the y value would be 1/2. Finally, the third region, we would have an x value of 3.5, or 7/2, and a y value of 1. Now what we want to do is we want to find the area of each region. Oops. Area of each region. So if I want to find the area in which M1 is located, I just want to find the area of this rectangle here. And you should know that rectangle is length times width, or base times height, either way. But in this case, 1 times 3 gives us 3. The next rectangle would be here. Again, finding this area, we would take 2 times 1, giving us 2. And then finally, the third rectangle would be 1 times 2, giving us an area of 2. So now what we can do is we can go on and we can find the centroid of a region. So in this case, I'm going to go ahead and find x bar. And from the previous slide, hopefully you remember that x bar is found by taking a sub x over a. So here, a sub x is just going to basically be the area times the distance from the y-axis, which is essentially the x coordinates. So in our first region, M1, we would have 3 times 1/2. In the second region, we have an area of 2 times an x value of 2, plus the third region, which is an area of 2 times an x value of 7/2. Now all of this goes over A, and A is simply the total area. So A is the total area. So in our case, it's 3 plus 2 plus 2, which is 7. So my denominator here is 7. When I simplify the numerator, I get 25/2 all over 7. This simplifies to 25/14 for x bar. I do the same thing for y bar. Y bar is found by taking a sub y over a, and a sub y is the area times the distance from x, or from the x-axis rather. So this area is 3 times the y value, which is 3/2, plus 2 times 1/2, plus 2 times 1. All of this is over 7 once again. In the top, we end up getting 15 halves divided by 7, giving me 15 14ths for y bar. I can write my centroid as an ordered pair. So x bar, y bar is equal to 25 14ths, 15 14ths for the final answer.